Welcome to FMSP Online Revision. This session is for OCR D2 and the topic we're going to be looking at is flows in a network. So we'll start by having a look at the specifications. So 5 points here. We need to be able to represent flow problems by means of a network of directed arcs and interpret network diagrams. Find the optimal flow rate in a network subject to given constraints. So you might have upper and lower capacities. Understand the meaning of the value of a cut. Use the maximum flow minimum cut theory and explain why it works. We might be asked to introduce a supersource or supersink when you have more than one source or sink, and replace a vertex of restricted capacity by a pair of unrestricted vertices connected by a suitable flow. And in Part E, we should be able to use the labelling procedure with arrows showing how much less could flow in each direction to augment a flow and hence determine the maximum flow in the network. So we're going to start by having a look at a question to draw out a number of these points. So this question from January 2011, so we've got a diagram representing a system of pipes through which a liquid can flow. The weights on the arcs show the lower and upper capacities of the pipes in litres per second. So which vertex is the source and which vertex is the sink is part 1. Part 2, cut alpha partitions the vertices into two sets, A, B, C and D, E, F, G, H and I. We've got to calculate the capacity of the cut. And if we just read through the entire question before we start, because it is quite long, then part 3 we've got to explain why partitioning in a slightly different way does not give a cut. Part 4 we've got to consider the flow along various different arcs and explain why they have the capacity that they have. And then in part 5, use the diagrams to show a minimum feasible flow and a maximal feasible flow. And then the last part, the upper capacity of BC is now increased from 8 to 18. We've got to use a diagram to show a flow of 19. List the saturated arcs when 19 litres per second flows and hence or otherwise find a cut. And then in part 7 we've got to explain how your answers to part 6 show that 19 litres per second is the maximum flow. So as I say, quite a long question, so we'll break it up into bits. So if we look at parts 1 and 2, so we've got our diagram. So the part 1 we're asked which vertex is the source. So if we look here we can see that there are flows coming out of B. So I think hopefully we would be happy that our source is B. So B is the source, and then we have a little look to see where the sink is going to be, and if we look we'll see that all of these flows go into E, so E is the sink. And then in part 2 it says cut alpha partitions the vertices into, and we have A, B and C. So this is our cut alpha. If we put that on and just label it, and then D, E, F, G, H, I, calculate the capacity of the cut. So remember that when we're doing that, we're looking at the maximum flows possible. So we have minimum and upper capacities, and when we're doing the cut, as long as they are going from the source to the sink, then we take their maximum capacities. Remember, if any of these had been going from the sink to the source, then we would have to take away the minimum capacities. But ours are all going from the source to the sink, so we have 4 plus 4 plus 4 plus 5 plus 5. So 22 litres per second. So 1 mark for the source and the sink, part 1, and then a method mark for getting your 4 plus 4 plus 4 plus 5 plus 5, and an accuracy mark for getting 22. And put in your units, litres per second. And we then come to part 3. Now part 3 says, explain why partitioning the vertices into A, D and G and B, C, E, F, H and I does not give a cut. So can we see that what you've got here, B is the source and it's in the right hand side, and E is also in the same set. So we haven't got a cut because the source and the sink are in the same set. So 1 mark for writing that down. So in order to separate correctly, we need to have the source in one set and the sink in the other. So part 4 says how many litres per second must flow along DG. So that's part A, and of course the minimum is 3, the maximum is 3, so it must be 3 litres per second. So that's an easy 1 mark. And then in part B, explain why the arc AD must be at its upper capacity. So its upper capacity is 4, and the reason is because we have to have a minimum of 3 going along DG, well in fact it has to be 3, and we have a minimum of 1 going along DE. Alright, so it must be 3 on DG and minimum of 1 on DE, so you need to have at least a flow of 4. So DE must have a flow of 4, and of course that is its upper capacity. Its upper capacity. And then it says, hence find the flow along BA. Now BA, you need at least to have, again, the maximum of 5, because you then want at least, you need 4 going along AD, and of course you'll have to have 1 going along AE. So that next bit says BA must be 5, since AD is 4 and AE must be at least 1. Since that's the minimum. So again, 1 mark for explaining why the arc AD was at its upper capacity, and then 1 mark for explaining why finding the flow in BA of 5. And then in the third part, part C, explain why at least 7 litres per second must flow along BC. So if we take I here, if we look at this, from I you need a minimum of 2 going to H, to H, and you need a minimum of 3 to E. So you must have 5 going in to I, so Fi needs to be 5, and then CE also, because remember you're having this flow going from B to C, so you need to have at least 5 to go along CF and F to I, but you also need a minimum of 2 to go from C to E. So CE minimum is 2. So that means starting at C, you therefore need at least a flow of 7 going into C. Okay, so that's from B. And again, you got 1 mark for considering the node I and the fact that it needed to be a minimum of 2 going to H and 3 going to E. And then you also got, so we had to have 5 going along CF and FI, and then you also got a mark for seeing that you had to have a flow of minimum of 2 going from C to E. So if we move on now to part 5, it says use the diagrams in the insert to show a minimum feasible flow and a maximum feasible flow. Now if we consider what we've said in the last question, we've agreed that we need a flow of 4 along AD and 3 along DG. And we also agreed in part 4 that that meant we would have to have a flow of 5 going along BA. We also found that we needed a minimum flow of 7 here, so that we had 5 going this way and 2 going there along CE. We needed 5 going along FI, so that the minimum of 2 could go up here and a minimum of 3 could go up there. We had to have a minimum of 1 here, remember, so we had a flow going from A to D of 4, so 3 went to G and 1 went to E. So all that information really came from doing part 4. So if we have a flow of 5 into A, then it'll be the minimum of 1 going in here. And we had 2 going into H, which means that we will just have nothing here, because we need a minimum of 2 going to G. And you've got a flow of 3 going into G and a flow of 2, so we'll have a flow of 5 there. Here we had a flow CF of 5, and then from F to I was 5, so there is nothing there. And the last one that I haven't completed, I think, is this one here, which needs a minimum flow of 2. So you got a method mark for starting off your minimum flow correctly, and then an accuracy mark for getting it completely correct. And then the second part of that question was to do a maximum flow. So again, if we use the same sort of information as we had the last time, we needed the maximum flow here, and we had a flow of 3 here. We had a maximum of 5 here, and we had our 1 and our 1. We had our maximums down here of 5 and 5, which meant that we had a flow of 3 here and 2 here. There was nothing left here. We only have a possibility of 2 going into H, so that had to be the minimum, and this had to be 5. So there aren't that many places that we can actually increase, really. But we have from B to C, we have a maximum capacity of 8, so we could increase that one. So that one I'll circle because that's been increased. If we do that, we could then have a flow of 3 going along CE, so that's been increased. and again the capacity, the maximum capacity along BE was actually 4, so we could, and we had 2 initially, but we could increase that to 4. So in actual fact we've really just increased those 3 flows. And again, a method mark and an accuracy mark for showing the maximum capacity, or the maximum flow, sorry. It then says for part 6, the upper capacity of BC is now increased to 18. So if we increase it to 18, use the diagram in the insert, so I have drawn that out here, to show a flow of 19. So we want to try and show a flow of 19. So again, we can put a lot of these that I've just copied through from the last slide. We could actually put a lot of these on. So I'll put these ones on as we had at the beginning, because they're not going to change. So I'll just copy those through. This is not going to change. This is not going to change. And again, these are not going to be able to change. So I'm just copying these all through. But at this stage now we have a maximum flow capacity of 18 rather than 8. So what we're actually going to be able to do here is we're going to be able to increase this slightly, because we had a flow of 3, but the maximum capacity was 5, so we could make that 5. This was already 5, so we actually can't change that. So although we have a maximum capacity along BC of 18, we're actually only really going to be able to send along a flow of 10, because we only have an outward total flow of 10. So we have now used the diagram to insert a flow of 19. So you've got 5 and 4 and 10, so that's 19 going out. And again, you can just check we have got 19 going in to the sink at E. It says list the saturated arcs. So in fact, if we consider the arcs that are saturated, so 4 is now saturated here, so AD, this is saturated, this is saturated, BC is not saturated, but CE is now saturated. So we just have to go through and make sure we actually, I'm just marking them in at this stage. This is now saturated, BE, and list them. So the saturated arcs should be BA, BE, AD, DG, CE, CF, and FI. So we have 7 saturated arcs. 1, 2, 3, 4, 5, 6, 7. Yes, so I have marked them on as well. So we then have got, hence or otherwise, find a cut. So what is the cut going to be? So we need a cut now of 19. So we will want to go, remember that the cut must go through your saturated arcs at this stage to get a maximum flow. So we could actually draw a cut through like that. So 5 plus 4 plus 5 plus 5, and we have then got a cut of 19. So the cut is, so we'll have BC on one side, and on the other side we will have all the other nodes, A, D, E, F, G, H, I. So 1 mark for showing the flow of 19, 1 mark for listing the saturated arcs, and 1 mark for showing the cut and listing it. And then the last little bit that we've got to do, we've got to explain how your answers to part 6 show that 19 litres per second is the maximum flow. So it's important here that we see that we've actually got a flow of 19. So part A up there meant that we have a flow of 19. So that means that the maximum flow is greater than or equal to 19. We have a flow of 19, so we don't want anything less, so we're looking, the maximum flow is always going to be greater than that. But in part B, we found that we have a cut of 19, and so that tells us that the minimum cut is less than or equal to 19. The maximum flow minimum cut theorem tells us that if we can find a maximum flow equal to a minimum cut, then we have our maximum flow. So 19 is the maximum flow. So there was a 1 mark for sort of writing down the fact that the flow of 19 meant that we had a maximum flow greater than or equal to 19, and minimum cut less than or equal to 19, and then we got 1 mark for remembering that maximum flow equals minimum cut. So our maximum flow is 19. So quite a number of marks for that question. I think there were 18 marks in total. It didn't, on the other hand, cover all the points that we mentioned on the specification, so I am just going to quickly look at a couple of slides just to remind you of some other things. You must be able to do what we call the labelling procedure, which wasn't included. So let's just imagine we have a diagram there showing water flowing through a pipework. So we're now going to show you how to do a labelling procedure. So each edge, will be labelled with 2 arrows. The forward arrow indicates the amount of excess capacity, that's the potential increase, and the backward arrow indicates the current flow. So let's just assume at the moment all the flows are 0. So initially the excess capacities are the full capacities. Right? So if we then consider how we might augment it, then we could see here that we could get a flow of 2. There's a maximum of 2 here. So the maximum flow along SACT that we could do is 2. So let's increase the flow by 2, which means we decrease all the arrows in the direction of this path by 2, and we increase all the arrows against the direction of this path. So our next diagram will look something like that. So that is what we refer to as the labelling procedure. So that's quite important that you're going to be able to do it. Now obviously you could do a lot more with this particular question, but we're not going to do that. But make sure when you do your labelling procedure that you cross out neatly so that we can see what's happening. The other thing that we might have to do is look at multiple sources and multiple sinks. So sometimes we'll need that. We deal with this situation by introducing a super source, which is here, and a super sink. So in the case of the super source, you've got 19 and 8 coming out of S1. So we must have 27 going into S1, and we've 15 and 17 coming out of S2, so we must have 32. Similarly over here, you've got for your supersync, you've got 10 and 12 going into it, so we must have 22 coming out here. You've got 16 and 3 there, so we must have 19 coming out there. And we've just got 12 going into T3, so we'll have 12 going into our supersync. And that just confirms those numbers. So I'm going to finish this session here and just remind you, as always, the way to revise your maths is to do lots of past papers and work through lots of questions.